Yeah. Yeah. Today is holiday, right?
Yes.
Okay, so today we'll discuss basically the Joule-Thomson coefficient and the Gibbs-Helmholtz equation and related some questions that we will discuss today. Probably it will be helpful. And few questions I have selected from this book. Or you can follow a book, probably that will be quite advanced, but you can follow for better understanding for thermodynamics. That is the Callen book.
Your voice was not clear.
Voice is not clear.
Yes, now clear. Then it was unclear.
Okay. So I was saying that you can read a book of thermodynamics that is the Callen book. Okay. So that is quite advanced level book. Means it's not written in general way, basically normal thermodynamics. That is a dedicated book for thermodynamics, classical thermodynamics and the statistical thermodynamics both. Okay.
Kellen.
Callen, I can upload the PDF of the Callen book, and that is available in Google as well. Just search the Callen book PDF thermodynamics, you will get it. It's quite difficult to read because it's written in different perspective, but it's very very good. It's best scientific way, because ad hocly just things are not introduced. You can read it, and but it is as you are in now BSc levels, it's better if you read it. You will get a great insight. uh, Generally these books are not recommended, or very rarely recommended, but still in the physics courses they recommend in BSc, but in chemistry generally they don't recommend. But it's very very good book, you can read it. Okay. So obviously, you can't understand everything written there, but don't worry about that. Just read it. Even I can't understand everything written over there.
It is available for free.
PDF is available, or you can buy it. It's not very expensive even. Um, Whenever you get some time, you can read it. It's like a mathematical approach you can think of thermodynamics.
Okay.
Thermodynamics is very not very easy actually. It's very complicated things. If you uh, really want to understand in terms of mathematical point of view, then it's not very easy thing.
Classical thermodynamics also.
Also, just think, ds a basically as entropy, that is a state function, whereas the heat, that is a path function. But we studied like that entropy is introduced to us as a elongation of that heat change, right? D cross q reversible by t. So they have you can read it and you can understand it. So there are few approaches are there. uh, okay, so let me start today. Let me first share the screen. Okay, let me talk on okay. Yeah. Mm. Okay. Is it visible right now? The screen is visible?
Yes.
Okay. Okay, so let me start with the Joule function experiment. Okay. First, let's say we discuss Joule experiment. So what was the intention to do this kind of experiment? That is, we know basically this thing really function of volume and temperature. I know this will probably
Voice is very low.
voice is low.
Yes. Can you please increase?
It is increased totally 100 is there. Why voice should not be? I'm using earbuds. It's connected. I'm not doing anything special. Usually, whatever I do, let me just turn off the windows 1 minute. Now is it audible?
Blue screen is visible.
Blue screen is visible, that I know. But my sound is now low or it's perfect.
It's perfect.
Okay. Okay. Then I don't know what. I just turn off the fan. Probably due to that fan. Okay. So you know that U is a function of volume and temperature, right? So from
Yes.
here, what you can write du or okay, du, not delta u. Du is basically you can write
Del
du.
U del V at constant T plus del U del T at constant
Exactly. These things you know, and we can identify this is CV.
CV and this is pi T.
So this equation we know. That is a general equation. That is not for ideal gas. That is not any pressure, constant volume, nothing. It's a general equation. Okay. But let's say if I want to calculate, if anybody want to calculate this derivative differentials, this coefficient CV or pi t, then how you can calculate? Okay, that is our matter of concern. Okay. So let's say first, if you want to calculate CV, CV you know how to calculate, right? It's a
Yes.
constant volume process. So if at constant volume, you have to increase. temperature by 1 degree Kelvin on 1 degree centigrade. For that, how much heat is required? That is the CV. How you can write it? You know that d cross q equals to du plus pdv, right? Now it
Yes.
is constant volume process, then dv equals to 0. So d cross qv is essentially du. Therefore, what you can write? Cv equals to, this is the definition of Cv, d cross q dtv, then it will be del u del dv. So this way you can calculate the Cv. This is a heat capacity at constant volume. Okay, so when you know the Cv, then from Cv you can calculate that internal energy change. Okay, for a change in internal energy. But okay, so let me write it. So then du will be Cv
CV delta T.
dt, and if you integrate it, then you can write del u equals to Cv del T if this is if Cv is independent of temperature.
Yes.
Okay, let me write it clearly. Independent of temperature. Temperature independent. Then you can do it. So these things you know. And just think this uh, CV basically heat capacity, right? So, but for it's a constant volume process. You have to keep in mind it's a constant volume process, and you are changing the temperature. You are giving heat and measuring the change in temperature. That's the whole idea, right? But in case of solid or liquid, that is these things are not valid basically. These equations, okay,
Why?
these are not practically applicable, valid, but you can't practically imply these equations. Okay,
In solid, there will be volume also be constant.
that volume basically the any attempt you make, uh, then what happens? A change in volume due to temperature rise will be there. Okay, just think because in case of solids, let's think solids are rigid, right? Rigid boundary solid has.
Yes.
So the constant volume process you can't uh, even perform there for solid and liquid. Volume will be increased. Okay, that's the thing. When you are changing the temperature, what happens in case of gas? Just you tight the nut bolts of the piston and you just increase the temperature. That imposes this condition, right?
Yes.
But in case of solid or liquid, how you can do that? It will
It will
break the
melt and
boundary.
increase the volume.
It that will expand, right? And after due to expansion, the boundary will be broken.
Yes.
So basic basically these formulas are general formula. That's okay, but practically you can't implement in case of solid or liquid. You have to consider a gaseous, at least partially gaseous system. Okay, but now the important thing is calculation of pi t. So CB you can calculate for gases. You know, this is not very
Yes.
difficult. But pi t, how you can calculate pi t? What is pi t?
Del U del V at constant T.
Tell you del P at constant T. So eventually this is a constant temperature process. That means it's a isothermal process. Correct?
Yes.
Okay. Now Joule tried to calculate this due to through an experiment. How he calculated that I'm showing. What was his experiment? This is something bath, a thermal bath types. Her liquids are there. Okay, any liquids are there. Here,
Ideal gas.
liquid, liquid, liquid is there, not gas. And here he considered something like this. Okay, and here is a piston cock. And this is filled with a gas A. Means A bulb. This bulb is A and this bulb is B. Okay, and here he has a stirrer. Okay, and there is a thermometer to measure the temperature. Okay, clear? This is the experimental setup.
Yes.
The voice is clear now?
Yes.
Okay. So this is the experimental setup. So now what he did that let's say uh, he just rotating this stirrer, and that's why the temperature will be dissociated in the whole bath. That's been the bath in the thermal equilibrium. That's you know. But what he did now, let's say the bulb, this bulb can A contains any gas, but it is at low pressure. Okay? So, but what happens? This B is vacuum. There is nothing. Okay, it's a vacuum. Clear?
Yes.
So when you just move this piston out, then what happened? It will be a free expansion. Okay,
No
so
work done.
no work done. Correct. So in case of free expansion, so you know d cross q equals to pdv equals to 0. Therefore, you can write it.
Yes.
It's not a constant volume process, nothing, but you can write it. Again, you are not giving any heat. You are not giving any heat. And there is a thermometer. Thermometer is reading, and thermometer reading is showing that T is constant. Temperature is not changing. If temperature is not changing, that essentially means it is 0. Because temperature is not changing, del T is 0. That is experimental reading. Clear? So du
Yes.
will be 0. Okay. Is it clear?
Yes. But the wall is adiabatic or not?
Which one?
The box wall, outer box.
Outer box, you can consider this isolated system. That thermometer is just measuring the temperature of the liquid.
In liquid and the gas chamber, there is no connection of heat.
No, thermometer is dipped into the liquid and it is measuring the change in temperature of the liquid.
Yes, that means no heat is transferred between the liquid and the gas chamber.
Yeah, yes, exactly. So that is why you can say d cross q equal to 0.
Yes.
And that is why du equal to 0 because that is a free expansion. So if du is 0, you know du is CVDT plus pi t del V, and
Yes.
it's a constant temperature process.
CVDT is 0.
Del T is 0. So CVDT part is 0. So you can write it as pi t dV. But dV is not 0. Volume is changing. For this gas, that is expansion, right? It's a
Yes.
free expansion, but that is expansion. So due to this expansion, del V is not a 0. So clearly,
Pi T is 0.
pi t is 0. So according to Joule experiment, the pi t should be 0. This is a real gas. This is not ideal gas.
For real
Ideal
gas
gas,
also pi T is 0.
no, that Joule obtained due to the experiment, but it was not true. You know, for ideal gas, pi t is not 0.
Yes.
Okay, so this called Joule's law. This pi t is 0. This experiment is called Joule's experiment. Joule experiment. But where is the uh, error that can you guess it? In this experimental setup, there must be some error, right? That's why he getting wrong result or he interpreting wrong. Where is the catch?
He is doing work done in the system.
No, that is a free expansion of gas. Work done is clearly zero. Actually, the temperature change is there due to this free expansion, na? Due to this free expansion, their temperature is changing clearly. But this expansion temperature is changing and pi t is not zero. Pi t is del u del v t. Correct?
Yes,
So that is actually as temperature is changing, del u is not du is not zero. D cross q is non-zero. Du is also non-zero, and that's why pi t is non-zero. But why the temperature is showing is constant? Because this temperature is measuring the temperature of the bath liquid. So let's say due to this expansion, very small amount temperature is changed, but but it is not directly measuring that temperature. It is measuring the temperature of the liquid. So that that small temperature change actually does not impact the temperature of the bath. Okay, it's just like that you are heating up, giving some amount of water to the sea. Then the water level of sea will not change, right?
yes,
Here also the same thing. That is the definition of bath basically. Because that heat is transferred from here to here. That is some amount of heating or cooling, anything it may be. That heat is transferred, but in the bath it actually dissolved. It just diffused in the bath, and that's why the overall temperature of bath did not increase or decrease. To change that amount of change in the temperature of the bath, you need a much more amount of heat. That is not considered here. That is a experimental failure. Okay, is it understandable what I want to say?
yes,
Okay, that's why actually there is a temperature change, but due to he was measuring the temperature change through the change in temperature change in the bath temperature. There is a problem. Okay, because you know that the formula, what was the formula? That m s del t equals to m
DQ.
prime s del t, right? This is a, then this will be for bath, this
Yes,
will be for that gas, but this s of the bath will be very very large, that del t will be very small for the bath, and mass of that huge amount of water, that will be also large. Correct?
yes,
So that is why the measurable change was not there in the bath temperature. Okay, so that is the problem. So now, later, did this experiment, which is called Joule-Thomson experiment. That is very important. By using this, you can calculate. This was a successful experiment, Joule-Thomson experiment. Okay, what Joule-Thomson did. First, let us understand the experimental setup again. Then only you can understand. Okay, first, okay, before experiment setup, what you wanted to calculate? Again, let's say first is we have to calculate the pi t. That is our, because Joule was trying to calculate pi t, right?
yes,
But he didn't succeed. So Joule-Thomson experiment also there to calculate this pi t, and one more quantity. Can you guess it? What was the thermodynamic equation state? One is pi t, another one is
JT.
JT. What is JT? No, no.
Joule Thomson coefficient.
Joule-Thomson coefficient is not involved in the thermodynamic equation state. Let me do. Okay. So here, just doing similarly, this was function of temperature and pressure.
Yes,
So CPDT plus this. Let's say we have to indicate something. How we can indicate it? let's say just giving a symbol gamma, any gamma TDP. Okay, just
What is this?
what is this means?
Pi T was internal pressure and it is
Oh, it's a volume,
internal volume.
not internal volume. It has a unit of volume. So not directly physical understanding is there, but it is a kind of volume. You can think like that because you know this expression. What was expression?
Which one?
Minus V minus B or plus B I think. Plus B minus del V del T P dt. Correct. This was the expression. Two expressions were there, right? For thermodynamic equation of state equal.
Yes.
First one is del U del V T equals to T times del V
Del
del
TP
T
minus
del
P.
V T. What I'm writing? These right minus
P.
P. And another one is del H del PT. So that was
P into
minus T
del
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 T del
P
T
del
P plus P.
plus P.
So this is pi T and this is let's say gamma T. And just giving the symbol. This is internal pressure, but this does not have any name. But it has unit of volume. You can see. Okay. So now, if we relate, now we know what we I want to relate that pi t with sigma t. If we want to relate these two quantity, then what? How we can relate? You know, dH equals to
du plus PdV plus VdP.
correct. So del H del PT. This is gamma t
Yes.
del U
Del PT.
or before that what we can write. Okay,
It is 0.
sorry. Let me write it in different way. TP plus CPDT. DH we can write it
Yes.
and DU CVDT
CVDP.
plus pi TDV
Pi TdV.
and this is eventually the
Gamma T.
so this equation we can write correct.
Yes.
Now if dt is 0 isothermal process if you impose then okay because isothermal process that's why constant t.
Yes. Plus V.
So this is the equation. Why isothermal process is considered? Because if you remember this pi t a gamma t there that is also for constant temperature, pi t is also for constant temperature, so you have to consider the isothermal process.
Yes.
Okay, clearly that's why. So this equation is valid. So if you know pi t gamma t, then you can calculate the pi t using this equation clearly.
Yes.
Now just understand it step by step. because later it will be getting something, some co- confusion may be created there, but just remind these steps. Okay. For ideal gas, you can check it. Ideal gas, it will be 0. You can check it. For liquid and solid, del V del T will be 0. By changing pressure, can you change the volume of any solid or liquid? That is
No.
incompressible, right? That is incompressible. So eventually then pi T will be volume,
0.
not 0, volume.
Yes, volume.
Okay. But we are not interested in case of solid or liquid. We have to calculate the pi. So for solid liquid, it is straightforward, the pi T. Not pi T, sorry, gamma T. Okay. Uh, we are interested to calculate gamma T for gases. So that's why now Joule experiment. How Joule Thomson experiment was defined. Let's see. These are the rigid boundary, okay? Isolated. Adiabatic boundary. Here, okay, here is a chamber. Okay, that is field of gas. Porous, this is porous. Now, uh,
Porous means semi-permeable.
semi-permeable. This is a piston-like thing. Here is also clear. Two gases are there. Here is one gas, same gas. Both are same gas. Okay, and we are measuring the temperature. Thermometer is not looking like thermometer, but here is thermometer. That is measuring temperature. Here also a thermometer. These two are temperature. T1, T2. Okay, and yes, and we can check the pressure of the gas as well. So here the pressure meter is also there. So here P2 and P1 barometer is there actually. So this is the experimental setup, correct?
Yes.
Okay. So now if this is the experimental, okay, it was disconnected. This is compressed in this direction, and if the compression is there, then this piston will move in this direction. Okay, so
Yes.
if this is this and this volume is v1 and v2, so this volume will be decreased and piston will move up to this point. Let's say just
To the porous plug.
so this is my initial condition, and when the piston completely move, then what will happen? Then it will not be there. It is moved to this position. Okay.
Okay.
Okay. So this position and this will also expand, right? This will also expand to, let's say, something like up to there.
It will not start from the vacuum. at the starting point of the porous
No,
plug?
no, no. There is some gas. There is some gas.
Okay.
Same gas. Same gas is there.
This experiment is not against vacuum.
Not against vacuum. There is a gas. That's why there is a volume, right? And temperature
Yes.
and pressure. Everything is there. Okay. So it moves. This is our final. Okay. So now, if you want to calculate work done, so work done at the left compartment, that will be PdV, integration over PdV, right? And the volume changes from V1 to 0.
Yes.
Clear? Now V1 is 0 and V2 is some, let's say V2. Nothing. I don't know. Okay. Oh, sorry. Beginning it was at beginning it was here. V2 is 0. But it like that. It's not vacuum, but it is as at 0. Like this. Okay.
This integration is 0 to V2.
0 to V2. Or you can think, okay, no, basically you can think like this way. There was no gas. Even you can think like that. Both is correct. Both is correct. But better, the experimental was like this. Experiment was like this. Experiment was like this. Okay, like this. Okay.
Okay.
So it is the right will be same, but it is 0 to V2.
V2
So it will be
minus PV1.
P1 V1. Why? Because here the pressure was
This is P1.
P1. Okay. And it will be
P2 V2.
P2 V2 because now the pressure is P2 here. So here as there is no gas, so is this does not make any sense. Let me clear it. Okay. Here there will be no gas, so this does not make any sense. Means thermometer is there, but there is no mean. Mm, okay. In book actually two pictures are not there, they just merged two pictures. That's why I draw like this. Okay. Now it is clear?
Yes.
Okay. So it is P2 V2 because now the pressure is P2 in this compartment and the volume V2 and temperature is T2. So what happens ultimately if you look at so total work done, if you calculate from here total work done, that will be P2 V2 minus P1 V1.
Yes.
Okay. So now uh, from first law of thermodynamics you know d cross q equals to du plus d cross w. So
Yes.
this total system, first I mentioned this isolated system totally. No heat is there, nothing is there. So as total system is isolated, so overall d cross q will be 0. Then du will be minus d cross w. Okay.
Yes.
So du means if you now integrate, um, then you will get u2 minus u1 and minus d cross w means P1 V1 minus P2 V2.
Yes, minus d cross w.
Okay, so P1 V1 is the initial condition and P2 V2 is the final condition. Here, this is what is the total internal energy? That will be U1 because that will come from this compartment only, and this is the U2. So what you can write? Okay,
H2 equals to H1.
H2 equals to H1. So this is an isoenthalpic process. So in this way, doing this amount of experimental brilliancy using, he just formulated a process which is isoenthalpic process. That's the important thing. This is an isoenthalpic process. It is not a constant temperature process. It's not a constant pressure process, but it's an isoenthalpic process. Okay. If you remember, d cross q p is actually related to the dh.
Yes.
So it is not isoenthalpic. So d cross q p is not a constant pressure process. Still del H is zero. Means total there is no enthalpy change. That is a reason. Okay. So now
Enthalpy is function of pressure and temperature only.
yes,
So if pressure and temperature is not changing, so enthalpy is zero, enthalpy change.
but here pressure temperature both are changing.
Temperature is constant along thermometer.
No, no. Here it is T2, here it was T1.
Okay.
It's not same. It's not same.
So how it is possible?
That you can see here. It is possible.
Sum of
Just
U and
because
PV is
it is
constant.
possible because this amount of how much work done is happening here, that is compensated by the internal energy change. So total internal energy means, let's say it is U1, okay, and it is U2, let's say some amount of internal energy in decrease. So that internal energy, how that internal energy can be decreased due to the expansion work done. There
Yes.
is no other heat exchange. That is the first law of thermodynamics, right? So then obviously internal energy plus work done will be constant, and that is the enthalpy. That's why it is a constant enthalpy process.
Is there any process where internal energy change is zero?
That you tried to do, Joule tried to do now. Joule was
Yes.
trying to do that,
That was
but he
failed.
did not succeed. Okay, he wanted to do, if you remember, what he wanted to do, he wanted to do du equal to zero. ISO ISO internal energy process he wanted to do, but he did not succeed.
Now
Okay,
there is nothing discovered yet.
it's not needed even because from here you can calculate it. Let me do it. From here you can calculate it. Probably there is there, maybe there, but that is not important.
Okay.
Okay, so if dH is zero, then we know dH equals to pi t dP
dp
plus Cp dt equals to 0. Therefore, del T del P isoenthalpic equals to minus 1 by Cp, then it will be, let me write it, pi t. Clear? Just check it.
minus 1 by cp into del h del pt.
That is pi t.
Okay, that is pi t. Yes.
So this is called Joule Thomson coefficient, mu j t. Okay, so that is actually what is what does it mean that is for this process, if the press how much the pressure change, that is the dp, then you can calculate the change in temperature, that is the dt. Okay, so del p del t it signifies that. So now if you can evaluate the mu jt, then easily you can calculate the pi t. cp you know for a gas easily.
Yes.
So if you know pi t, then easily you can calculate this gamma t. That's the important thing, right?
Yes.
Actually, that is gamma t even. I just did it wrong. This is not pi t, this is gamma t, sorry.
Yes. Del H del PT. Gamma T.
So now if you know the gamma t, then easily you can calculate the pi t. So no needed to do iso internal energy process. So from here you can directly calculate. Okay. But it is for the real gas. Ideal gas, if you calculate, it will be always zero.
This gamma T part.
Not gamma t part, this mu jt. Mu jt is zero, that means gamma t is always be zero because Cp is not zero eventually. Okay, then it will be zero. How you can check it for ideal gas?
From PV equals to NRT.
Yes, from if you write this, so how you can write it as, you know, this already we have derived del v del pt pi t plus p v. Okay, pi t for ideal gas, pi t is zero,
Yes.
so it will be, and del v del pt will be n r by p. Correct.
NRT by P.
Not t by p. No, del v del tp.
Okay. This NR by P.
Let me do it, or I've done something wrong. Del v del pt. Sorry, del v del pt. Sorry. So it is first part is zero, second part is nr t by
P
p
square.
square, and b equal to nr t by p.
NRT by P.
So gamma t is zero, so mu jt will be zero. So for ideal gas, it is straightforward, it is zero. But for van der Waals gas, we can calculate it. That is important.
Why we are calculating for Van der Waals gas?
We can calculate for any other gases, but experimentally we can do that. But if you want to do analytically, theoretically, then you have to consider an equation. So that can be
Van der
done
Waals is
by,
not real gas.
yes, van der Waals gas not real gas, but it's a better agreement to real gas, right? Compared to ideal
Yes.
gas. There are other equation as well. You can consider those even. But in your syllabus, it is van der Waals gas. Okay, that's
Okay.
the important. And you can check how much agreement is there with the experimental value, because experimental value is the for real gas. Exactly, for the real gas, that is experimental value, and this is a theoretical calculation you want to do considering the van der Waals gas. So by comparing those two data, you can uh, you can get an understanding about the how good van der Waals gas uh, as a real gas. Okay, So then you can think.
Yes.
You can draw a map. Okay. So before that, we can calculate it. But before that, how this mu zt can be calculated more convenient way, that you know how. Just we have to invoke the pi t equation that we have already written. What was that? This is pi t. So it is minus pi t will be t del v del tp plus minus v, right? So just let me write it. So it will be 1 by cp and t del v del t v minus v.
Minus V.
Okay. Now it is easy. For Van der Waals gas, you can calculate it. For Van der Waals gas, E plus
A by V square V minus B equal to RT.
for 1 mole, obviously, for 1 mole. Then it will be, now how can calculate del V del Tp?
Change it to volume expression.
Okay, guide me how we can do it.
Multiplying these terms PV.
Okay, Pv minus Pb plus A by V minus AB by V square equals to RT. Then can you calculate? Can you calculate? You have to write first V equals to something, then you can do.
Yes.
Is there any other option?
If I differentiate with respect to V and T,
If you want, if you differentiate,
with respect to PV and T,
okay. So better not to do that. Do del P del Vp. This you can do, right?
yes,
So T is just 1 by R. So you can write P plus A by V square V minus B by R. So del T del V P. So that will be, so you can write it P V minus B by R plus A by R V square V minus B. So first term will be just P by R and second term will be, there are two terms. So first it will be A, sorry, del V of A by RV. The last term will be 2AB by RV cube. Correct?
yes,
So it is eventually, this is this.
yes,
So take the 1 by R out. Then it is P minus A by V square minus 2AB by V cube. So, and now you can invoke the P. P you know, P is RT by V minus B minus
A by V square.
minus or plus. Something is wrong. Okay, let's see. So It is not cancelled. Okay, okay. Equal handle as it is. P you can keep it as it is. So it's okay. So this is the value. Yes, it's the value. Hmm, 1 minute. Let me check.
The last term will be positive.
This term. That will be positive. No, actually that will cancel. Nothing will be there actually. Okay, let me check. 1 minute.
If it's p plus a by v square, then it's correct.
Then to you just replace it, but that will not. RT. Okay, then. Hmm, is there? They are using actually this value. This is no, this not this. Actually, del T del VP. Okay, no. Yes, del V del TP, right? This del V del TP is written as uh, R by P minus A by V square. Means this part is not there. So that's why I'm looking. Is there any mistake or not? Probably they have just ignored because A, B are multiplied. Okay, that's the case, I think.
I have done something in my college
Mhm.
expression like that, and
Mhm.
there is p plus a by v square minus that part 2a by.
Let me check in the book. Wait. It's better to check in the book always.
By differentiating the expressions.
Mhm. One. This is the Joule Thomson school, right? JQ. Okay. Hmm. No, they just wrote down. It will be there, I think. Just give me a minute. I have done this before. For Van der Waals gas, we can calculate it. Not that much difficult. Yes. Del V del PP, right? Hmm. Here is okay. So yes, actually they are considering this, um, ignoring this part. Yes, I'm correct. This part they are ignoring. Okay, due to A and B is there, they are ignoring this part. It should be, otherwise nothing is wrong. Okay.
Why it is ignored?
Okay, A B book. You, if you remember the values of A and B, what is the values? They are very small compared to P and V. If you remember,
Yes, but V is in the denominator.
and that is Q. So think the term will be very less, correct?
V is
A,
very very greater than B, but not greater than A.
no. A is 10 to the power minus 3. B is 10 to the power minus 3. And V is also greater than these two. And VQ. Then you can think now what will be the value. In last class, we did some example of Van der Waals gas, A and B. If you remember those values, then you can check it.
Yes, so VQ should be neglected.
VQ should be neglected. Na? AB is small. VQ is also small. So it's overall very less.
Yes,
Uh,
overall it should be 0.
Not zero. It's very less compared to these two values. That's why.
Yes.
That's why they have considered. Otherwise, you can consider it. If you do exact calculation, if you want to do exact calculation, then you should consider this part as well. Okay, that you can do also. Then the expression will be more complicated, but the exact result you can get. Okay, so what is mu jet? Cp and this. So 1 by Cp.
T into del V del Tp minus V.
Hmm. So T RT square minus V. Is it correct?
Yes.
Okay. So what you can write now? Just let me calculate this part. Then it will be RT by.
P plus A by V square minus 2A by V square.
Hmm. You have done this in class, right?
Yes.
Hmm. So it is okay.
Yes.
RT, just take it above, then it will be just hmm. So if you take V minus B common, then it will be 1 minus 2A. Okay, okay. Here it should be okay. Here V minus B also taken there, so it should be here V minus B. Okay,
Okay.
and again you see this is V minus B, and here it is V square, so it's eventually less than
1 by V.
V. Yes. So what you can do, approximate it.
Yes.
So you
1
have to
plus
do
2A by RTV.
hmm? No, just do it like this. V minus B plus 2A V minus B square by RTV square plus V. Plus, not plus, minus B, sorry. So the VB will be cancelled out. So it will be just minus B and this. Okay. And it
Okay.
can be written as minus B plus 2A by
2A by RT.
2A by. So you see this expression is after two, three approximation is there. After that, it's not exact. So mu GT is eventually 1 by Cp times 2A RT 2A by RT. So this is our Joule function coefficient. So now, if now we will have three cases. We can have three cases, right?
Yes.
First case, 2A by RT is greater than B, or uh, don't do it like this. Let's say mu jet is positive. So if mu jet is positive, that means mu jet is del T del P
Constant
H.
H.
That is positive. And if you remember the experiment, the pressure was decreasing, right?
Yes.
dP was decreasing. Let's say if the pressure is decreasing, it is changing from P1 to P2. If dP is, let's say if del P is negative, what does it mean? If dP is negative,
Del T
that
also
means
negative.
del T also negative. Eventually it is cooling.
Yes. Cooling.
Okay, so when Vgt is positive, it should be cooling. Okay, so that means T2 is less than T1. Okay, it's okay. When mu Jt is negative, that means this is negative. So dP is negative, so dt should be positive, right?
Yes.
So it is heating. So when this cooling will occur, so when mu gt is negative and mu zt is negative means from here you can see, sorry, positive. That means, okay, before that, just let me complete it. So and when mu zt is 0, that means dt is 0, right?
Yes. No temperature change.
No change.
Isothermal.
Exactly. So this is so when this will occur, this will occur when clearly 2a by RT equals to B. Now the T will be 2a by
RB.
RB, and this temperature is called inversion temperature.
Yes.
Okay, so why this is called inversion temperature, that we can understand now. So if the temperature is 2a by RB, then obviously there will be no heating or no cooling, no change.
Yes.
But here, if you see, if when mu jet is positive means 2a by RT is greater than B, correct?
Yes.
That means you can write it T is less than
2A by RB.
2a by RB, and 2a by RB is actually the inverse temperature, so Ti. So that means if it is less than Ti, then cooling will occur. And similarly, here you can write if it is greater than Ti, then heating will occur. That's why it is called inversion temperature. Okay,
Okay.
I think it is clear now.
Yes.
If you plot, then it will be very much clear. Yeah. Just a minute. Hello. यस। हाँ हाँ ठीक है, बट अभी मैं मीटिंग में हूँ। आप 1 घंटे बाद कल कॉल कर सकते हो? ठीक है। ओके, सॉरी। ओके। Okay, so now if you plot tip T by P or P by T, what was the plot? T by P, correct. So pressure is decreasing, right?
Yes.
And pressure is decreasing, and let's say there is a inversion temperature, something like here, that is the Ti. So if it is less than Ti, then what will happen?
Cooling will occur.
Cooling will occur. And cooling will occur means the slope will be positive, correct? So it will be
Yes.
like this. And after inversion temperature, it should be like this. It's not straight line.
Heating occur.
Heating occur and slope is negative. Okay,
Yes.
this is the case. This is the inversion temperature. Again, you can have for another inversion temperature, you will have like same kind of graph. Here, let's see. Here also, this kind of graph you can obtain. Okay, so
For
these are
different inversion temperature.
for different inversion temperature. For different inversion temperature. So you see this inversion temperature eventually makes a graph like this. If you just plot the inversion temperatures, then you can have, I'm not, it's not drawn properly. If you draw it properly, then it will gives you like this. So it's like this kind of. Okay, so this is the plot. This is the variation of inversion temperature. Okay, so is it clear?
Yes.
Okay. Okay, so I think this is no, nothing is left for the Joule Thomson coefficient. That's it.
Is it related to producing low temperature?
Producing low temperature means?
Cryogenics. I was reading a science book where
Hmm.
it is written that helium gas is used to
Okay, that's
make
what I'm saying.
low.
In case of helium gas and hydrogen gas also, this inversion temperature is very low. Okay, so always in nature, in normal temperature, it is actually 80 Kelvin like this, below 100 Kelvin. So you can see in general case, general temperature, room temperature, these are way beyond the inversion temperature, correct? So
Yes.
always it will be what? Heating or cooling? Heating.
Heating.
Always there will be heating in case of hydrogen gas. Okay. So I'm just saying the inversion temperature. Oh, for helium it is 40 degrees, 40 Kelvin. Hydrogen gas it is 200 Kelvin.
So how they produce low temperature? That means they are produce heat.
How they produce low temperature means?
They are used to produce low temperature.
No, that is a different thing. That is a different. Yes, helium gas is used. Helium gas is used to produce.
Rapid expansion of helium gas
Huh.
produces low temperature.
Yes, yes. That's from the thermodynamics. You see, when expansion is occur, what will happen? Rapid
Cooling.
cooling will occur. Now that is a different thing. That is not related to inversion temperature. You have to keep in mind inversion temperature is for the isoenthalpic process. Everything you are uh, discussing, we're discussing here, no? This is everything for isoenthalpy process. That's you have to
This is
keep in mind.
different from normal expansion. It is Joule-Thomson expansion.
Yes, it's Joule-Thomson coefficient. This is not normal because normal expansion is need not to be isoenthalpic. Yes, if the expansion is isoenthalpic, then obviously these things will be there. Otherwise, no. Okay.
Can I practically do this experiment
Mm-hmm. You cannot, but practically doable.
in IITs?
I don't know because these experiments done way before. There's 100 years before, right? I don't know exact timing. If there is written in book, actually not written, but you think this is way beyond. So today, though, you can do it easily. Nothing is there.
These inversion temperatures are determined experimentally or theoretically?
Experimentally, because this is for this calculation we done. This is for van der Waals gas after doing approximation.
Yes.
Experimentally they done. They check actually. They just check change the pressure, decrease the pressure, and calculate the slope. When the slope is zero, that is the inversion temperature.
Inversion temperature means where temperature is constant, neither heating or cooling.
Inversion temperature means when mu will be zero. That means slope is zero, not temperature is constant. Okay.
Okay.
That means you are changing. That's the point. Inversion temperature is a point. You see here, if you change the pressure also, then also the T will be zero. Dt will be zero. That's the inversion temperature. Mu jet is zero. Slope is zero. Mu jet is the slope, right? Del T del T. And in a curve, slope is zero means what? That's the point or the minima or maximum. You have
Point
studied
of
this.
inflection.
Yes. In terms of mathematics, if you want to say that is the maximum. Here it is max. Okay.
Okay.
Now this part completed. Second part gives as much. Let me do it. Gives as much equation. Okay. Okay, we have discussed that gives as much equation. Then I was correct. Nothing wrong was there, but some mistake we had done actually. That's why. Okay, just remind. I have to. Okay, here it is written. Okay, one. Yes, these things I have mentioned clearly. There are few problems regarding this rule function, but okay, if time permits, then we can do. Otherwise, it's easy, just formula based. You have to remind that formula, then you can do it. But now, yes, we will discuss this rule function. 1 minute. Gives Helmholtz equation. Sorry. So you know from Bg equal to Vdp minus
SDT.
SDT. So clearly del G del T
Del Tp equal to S minus S.
mass minus. Okay. So again, also you know these things.
Yes.
So S will be So minus s will be g minus h by t. Okay. So this is one of the Gibbs-Helmholtz equation. Okay. I think it's
Okay.
easy. Or you can write g equals to
Del
h
H
plus
plus T into del G del P.
exactly. So this is one of the equation. But we generally deal with the changing Gibbs free energy like this. So this is the uh, change of Gibbs free energy with respect to temperature, that will be equals to g minus h by t. Now, yes, we are considering a process. Let's say a process that is changing A to B, and this change is, let's say, del G, correct?
Yes.
And this occurs at a temperature T. Now we change the temperature of and carried out the same process, and now temperature is T plus dt. Then surely this will be now del G prime. That will not be same.
Yes.
Okay. So if that is true, then if we want to calculate what will be del G minus del G prime. Del G prime minus del G. That is eventually delta of del G,
Yes.
because this is infinitesimal small change. You can write it as del G plus delta of del G, because we are changing the temperature very small, so it should be very small change. Okay. So we want to calculate this because we are changing ultimately the temperature, correct? And everything is constant
Yes.
pressure. Let's say everything we are doing at isobaric constant pressure. So now what
Minus delta S.
delta G equal to delta H minus
T delta S.
T delta S. So T delta S and it is delta T. So what will happen? Or you can do it directly, not that's करने का जरूरत नहीं है. So how we can do it? So here this is for G. So delta G, it will be just delta H plus T into delta T. You can directly do it. But in formal way also,
It will be minus delta S.
it will be not minus delta S, just delta S. One minute. Yes, minus delta S should be minus delta S. No, but yes, you are just giving a delta sign there. I just don't want to do that
Yes.
one. I just don't want to do that. 1 minute. There should be a because uh, we are differentiating these, right? So delta G we can evaluate in a better way even 1 minute. I have done this. I have done this. So how we can write it? This is for delta G, right? So del of delta G. So let's say this is actually uh just do it in this way. So it is eventually delta G minus this. So this delta G prime, this delta G prime is eventually a change in Gibbs free energy, correct? So change in Gibbs free energy, if you differentiate with the temperature, yes, then you can, yes, it will be there. So if you dt, so then it is eventually a change in temperature with respect to temperature. So that will give us entropy. So it will be okay. And just see this equation is correct. So you can calculate the entropy. Just it is del G del T P, right?
Yes.
Okay. So for this process, there is the entropy change. Sorry, Gibbs free energy change.
Yes.
So that Gibbs free energy for this process only, not a change between these two processes. That I am not considering. That I am not considering. Let's say this change is also very small. If that is the case, this delta G, then you can calculate the entropy at this point. Just focus. No, it's not difficult. Just focus this. It's just only this process at T occurring this. Then for this process, I can write S entropy equal to like this. This I can write. This I can write.
Yes.
Okay. So let me write it as S. And for second process, when it is T plus dt, then it is, let's say, S prime. So it will be like this.
Yes.
Okay. So what is the change in enthalpy? Sorry, and not enthalpy, this entropy, then it will be S prime minus S.
Yes.
So it is minus of delta G del T min plus del G del Tp. So it is minus delta of del Gt at constant P. Okay. So you can write it.
Okay.
I think it's clear.
Yes.
So if you can write it, so eventually, finally you can write this equals to minus delta S, and minus delta S is del G minus T. Or you can write okay. So this is the Gibbs-Helmholtz equation. I think it's now clear.
Yes.
But there is another form. You can write it as del Gt equals to del Ht plus this. Now, if you want to calculate, in order to calculate this, so this will be, how you can do it? Just first take 1 by T out.
Minus del H by T square.
Yes, if you want to do formally, then it will be like this, if I'm not wrong. Okay. And this value, this value already we have calculated here. Just put it. So it will be 1 by T delta G by T minus delta H by T. So it will be minus delta H by T square. This is another form of Gibbs-Helmholtz equation. Okay,
Okay.
you can write it. Or there are another form that also you can do. This. So how you can, if you want to calculate, how you can calculate it? So you
Plus
can
delta
calculate
H.
it as
Just change the denominator variable.
like this, correct?
Yes.
Or you can do it like this,
Yes.
and this is minus
1 by
1
t
by
square.
T square. Or if you take it above, then it is just T square. So minus T square, correct?
Yes.
And this part is already delta H by T square, so minus will goes away, and T square cancels, so it is just delta H.
Plus delta H.
So this is the base form. Base form of the Gibbs-Helmholtz equation. Okay.
Okay.
So this is in terms of Gibbs-Helmholtz. So you can calculate similarly for the Helmholtz free energy. This is Gibbs free in terms of Gibbs free energy, or you can already calculate for the Helmholtz free energy following the similar procedure. I'm just writing. What will happen? Just instead of G, it will be A, and instead of P, it will be
V.
V. That's it. And H will be replaced by.
U.
So that I think you can do. Just follow from where you have to start. You have to start dA, equation of dA. From there you can do it. Okay.
Yes.
So I'm just writing the Gibbs-Helmholtz equations. There are three equations that we have derived just now. First one is del G
A
equals to del H plus
plus
P.
T. Del G del T constant P.
This is one form. Second form is
Del T of del G by T.
this equals to minus del H by
T square.
T square. And third form is
Del G by T. Del 1 by T equal to plus del H.
these three. All are constant pressure. So analogous form of Helmholtz free energy will be, first it will be del A will be del U plus T delta A delta T
V.
at constant volume. Second form will be del A by T
Del
by T. Constant volume is minus del U by
del U by T square.
T square. And third form will be delta U. So these are the Helmholtz free energies. Okay. So now we can solve that problem which we did last time. That we'll solve today. Then everything will be completed, I think. Yes. What was the problem? Okay, do it first. For the reaction Which reaction? Del G 0 at 298 Kelvin is okay, and we have to calculate the del G 0 500 Kelvin, considering this del H 0 is constant. This we have to calculate. Okay,
Okay.
how we can approach this, you know?
G by T.
Okay, so okay,
Yes.
is it clear?
Yes.
Okay, so it will be minus 1 by T, so just 1 by T. Okay, just check I'm doing it correct or not. Okay,
Yes.
this value is given. This is at 298 Kelvin. So this value is minus 16.45 kilojoule divided by 298 plus del H. This is minus 46.11. So it is, and this will be 1. So calculate it.
First one is minus 0.552.
Minus
0.0552.
0.0552, and this one
Minus 0.0955.
is, I'm not
Yes.
checking.
Okay.
So what will be the total?
Minus 0.150.
Minus 0.150.
1507.
Okay, so delta G prime that we have calculated, we have to just multiply the 500. So what is the answer?
minus 75.387.
Minus 75.387.
Yes.
So my answer is not matching.
1 minute, I am rechecking. Second part is minus 0.0625.
This one.
Yes, 0.625,955. No, no,
What is? It is
0.0625.
positive or negative? That you have to first check. Because um, now this would be positive, right? Because this is the what will be this? This will be this is small number, this is big number, so it is positive. So check it correctly. Let me bring my calculator.
Yes, it's positive.
It is plus actually plus 0. Yes, 0.0251. It is correct. 16.45 wala.
Yes.
Hmm.
Answer is 3.655.
Hmm. So it is plus 7.308 into 2.
731. Yes. 3.6557.
So you see at 298 Kelvin it is favorable minus, but at 500 Kelvin it is not favorable. This
Yes.
reaction. Okay. Okay. So let us do another example. This example you should do and just you have to tell me the correct answer. You have to try it. Same procedure, everything is same. After this, we will solve a question from rule Thompson, then everything will be completed. Do it. You have 3 minutes.
minus 148.052.
Yes. Good. But still, let me do it because yeah, you have to use this formula ultimately. Correct.
Yes.
So everything is given, I think. Yes. First one is minus higher temperature 35. Okay, correct. 7, 6, 8. 35. Correct. 35. So 35 degree means
308 Kelvin.
so by solving this you can get the answer. Correct. So what will be the answer? Just let me do it. What is this value? Just show me the values. It is minus 0.2716. It is minus
0.2878.
in this one. So okay. So this is the answer. Okay.
Yes.
Now I think Joule summation coefficient is okay. Okay, we can solve one question from Joule summation coefficient and Gibbs Edmond part is done. So let me solve the last question from Joule summation part. So that Ti equals to alpha I inverse for ideal gas. Great question. Do you have solved this question?
No.
What is alpha? Alpha
Expansion coefficient.
expansion coefficient alpha I is I is there 1 by V
Del V
del
del
V
T at constant P.
del T. So do it. So how we can do it? Ti is 2A by
2A by RV.
RV, but that is for Van der Waals gas. You can write it. This was del V del P. Check what was the form.
1 by Cp T into del V del Tp minus V.
Okay. So now at inversion temperature, it is 0, right? So when it is Ti,
Yes.
it is 0. Cp is not 0. So eventually it is 1 by V, just straightforward.
Yes, I got it.
Okay. So we have time, so we can discuss one more question. There are lots of questions, but discuss one more. Calculate μJt of CO at 28 Kelvin and 40.53 megapascal pressure. This value is given T by P times del V del T P. This is 0.984 unitless. The molar volume is given 76 centimeter cube per mole. Everything is given, just you have to calculate. Cp is 37.28 joule per Kelvin. Okay, right. Nothing is there, just you have to calculate. What is μJt?
1 by Cp T into del V del Tp minus V.
Okay, just take V out. Everything is for molar, so it's molar, obviously. So molar volume is given, that is 76 centimeter cube. Okay, so centimeter cube will be there. Mole inverse will be cancelled out. Cp is 37.28 joule per Kelvin. And this will be unitless. This value is 0.984 minus 1. So eventually it is negative. Okay,
Minus 0.27.
minus.
Sorry, I forgot the unit conversion.
Here you can directly do it. This is correct.
Yes.
This is unitless. So it is 1 minus something. So it is 0.9, 0.984 minus, what is happening? 0.984 minus 1. So it is eventually 0.016 minus. So minus this into 76 into, not into, divided by 37.28. So it is minus 0.0326 into 10 to the power 6 joule inverse meter cube Kelvin. These things is there, but we need in what? We have to change it, right?
Yes.
We have to change it ATM. So that we can change. But this unit is also correct. This pressure is given. Pressure is not needed even. pressure, temperature, nothing was important. But this answer is also correct. Nothing is wrong.
They are given to confuse.
Yes, they just give that unit, but you can do it in terms of ATM. This you can convert into ATM, but that is not important. Just by using the relation of R, you can calculate. The answer is correct. Okay,
Okay.
you can try it. It will be just 26 Kelvin.
I am also getting it.
So you can do it. Okay. So now I think it's all done. Okay. So let me stop sharing. Okay. So now if there are any doubt you have, you can ask me in WhatsApp. Okay.
Okay, thank you.
Yes. And do your study. Okay. And whenever you have any doubt, you can ask me, or if I take any other course, if I assign TA for any other course, then I will again let you know. Okay.
Please inform me.
Okay. Okay. So best of luck. So which year you are now?
Second year, fourth sem,
Second year, fourth sem. Okay. Okay. From which college and which university?
Bakura.
Bakur University. Okay. Good. Okay. So do it. Okay. So if you face any problem, not only regarding this thermodynamics, any problem, you can ask me. Okay. I will try to solve. I will try
Another
my
topic
best.
also.
You can ask me if I capable to solve it. I will solve. I can help you. But for inorganic, organic, probably I forgot everything. But if it is in physical, then I will try to help.
That I do not need. Only physical I need.
Okay, then I will try. Obviously, I will try. If I remember, I will try. Okay.
Please send the remaining questions.
From which part? Is this gives much?
Yes, and from the whole course that are not done in this class.
Okay. Okay. I will share you the note, mm, the questions from where I was selecting the questions that I will share, and from there you can do it. Okay.
And the book also.
Yes, that I will upload. Surely, that will upload. Okay.
Okay.
Thank you for joining.